Bueno, entonces vamos a comenzar con el seminario de Ingeniería Matemática y Computacional. Muchas gracias a todos por conectarse. El día de hoy tenemos como invitado a Digvijay Boob, que es profesor asistente en Southern Methodist University en Texas. Digvijay obtuvo su PhD recientemente, en mayo más o menos, en el programa de Algorithms, Combinatorics and Optimization de Georgia Tech, bajo la supervisión de George Land. Y bueno, Digvijay ha hecho trabajos muy interesantes, tanto en optimización convexa como no convexa, que fueron básicamente método de primer orden, fue su tema de tesis. Y producto de ello, obtuvo una nominación como finalista para el premio del Optimization Society de Inference para investigadores jóvenes. La charla de hoy se concentra en métodos de primer orden para algunos problemas no convexos, pero estructurados para optimización con restricciones funcionales. So, thank you, Digvijay, again, and yeah, go ahead.
Yes, thank you, Christopher, and thank you all for joining this talk. Today I'm going to talk about the first order methods for some structured non-convex function constraint optimization problems. This is my joint work with co-authors Chi Deng, Josh Lan, and Yilin Wang. So the outline is basically in the first section, I'll introduce the problem and I'll also introduce what is the structure that we are imposing. And in the second part, I will present a feasible proximal point method for this function constraint problem. In the third section, I will show some empirical studies and then we'll conclude. So what is the problem of interest here? We want to minimize this function psi x subject to the function constraint gx less than equal to eta. So in this presentation, psi x is a mu weakly convex function. It could be non-smooth, non-differentiable for that matter, but there exists constant mu such that provides a lower bound. So if you see when you put mu is equal to 0, this turns out to be a convex function. And mu weakly convex basically says that it could be non-convex, but there is a lower curvature bound of mu there. And the constraint function gx is a non-convex function which has the following structure. It is the difference of two convex functions, g bar x and hx, where g bar is a convex continuous function and hx is convex and continuously differentiable function. Okay.
Oh, one question. So
yes.
Psi then differentiable, right? That's
not necessarily. So you can have basically non-smooth non-smooth convex functions and a non-convex smooth function, and their summation would be basically a non-smooth weakly convex function.
But then, I mean, the psi, what is
psi
it?
prime?
Subdifferentiable or what?
Subdifferential, yes. So think of it this way. So assume that psi x has this mu lower curvature, right? So if you add mu by 2 times x square, for example, then this becomes a convex function, right? So now this convex function has subdifferential.
Yes.
Okay. So you can think of this subdifferential as a Minkowski sum of subdifferential of the psi, like psi itself plus mu times x.
Yeah.
So if you do a Minkowski reduction of mu times x, you will get the subdifferential of this.
Okay, thank you.
And they will satisfy this condition.
Right.
So this is something we defined in our paper earlier. Like this is our old work. Let me turn on the do not disturb. Yes. So yes, but here I didn't go into it, but it's a good question. Yeah. Thank you. And please feel free to ask questions anytime in between. Okay. So what are the motivating applications? So the application that we consider here is a sparse optimization application. So basically you are given some finite sum objective subject to a sparsity constraint. So in literature, generally you do a convex relaxation of this non-convex sparsity constraint. You can either make it as a constraint problem, or you can also put it in the objective with some Lagrange duality multiplier, and because let's say in most of the cases you are looking at these problems under a convex objective, so the convex duality holds, and in that case these two are equivalent. Okay, so in that sense, if you increase the lambda, you will decrease the in some sense you will decrease the bound on the constraint. So such a relation holds for a convex problem, but there are also non-convex relaxation of this L0 constraint. So just to give you an idea, in that case, Gx basically becomes lambda times L1 norm of x, which is like again lasso type, but then you reduce a convex function, actually a smooth convex function from that function. Okay. So there are many examples of this which are proposed in the literature, which are like motivated from statistics. Statistical studies of the sparse constraint problem. So there is MCP, SCAD, X. So you will see in this case, basically the function form is just lambda times norm of x minus hx, right? And all these different types of function, they have some hx, which you can actually write it down as a smooth function. Okay? Even for LP between 0 and 1, you can smoothen it. Generally, you smoothen it out with an epsilon, which looks like the following after that. Okay? This is the LP term after you use this value of lambda and h. Okay, so now that we have it, we can look at these figures and why we think that these are better. So this is a little bit from statistical point of view, but basically in an L1 norm function, when your coefficients are large, the bias introduced in the objective or is quite high, and these non-convex functions, specifically those which flatten out, people have proposed these essentially to take care of these bias terms when the coefficients are quite large. So that is at a high level, but basically when you want these functions to flatten out, naturally they become non-convex, and this is like if your slope is large, then it just becomes a very good approximation of L0 norm, because L0 norm basically is 0 at 0 and 1 everywhere else. So the approximation becomes tighter and tighter. Of course, the problems become harder to solve, but now you have a continuum of functions that you can really use to get better approximation of L0 norms, and you can decide whatever is the best, whatever works best for your application. Okay. So our experiments later on will be mostly with respect to MCP, but like with respect to SCAD and XP, you can get like similar results. Okay. We haven't really performed experiments with respect to log and these LP functions, but I suppose it will be similar. So these non-convex relaxation, as I said, they have become popular. Okay, but in the literature, most of the works for solving this non-convex relaxation is when you put these like non-convex penalties in the objective, because people don't want to deal with non-convex function constraints in general when they want to solve problems. But the problem with this kind of formulation is that there is no duality. So we can't necessarily say with the surety of coming from theoretical point of view that when you increase the lambda, your value of the constraint will go down at a first order stationary point, because we don't necessarily find an optimal point in that case. So our problem here is basically now modeling this problem as, rather than regularize, actually model it as a constraint problem, where you want to enforce the constraint. You want to make sure that the final solution in output is actually feasible. Okay. In this case, the constraint function is non-convex, non-smooth. So the popular methods like gradient descent for or projected gradient descent, which require efficient projection oracle, they don't work. So can we design some algorithms to solve this problem efficiently? That's the question. So in the related works, there are some notable points that I should mention here. There's a lot of work that has happened classically in nonlinear optimization, but because it's a non-smooth optimization, this is not a continuously differentiable function. So those works don't necessarily apply as it is. Recently, people have started looking at like majorization, minimization, and DCCP kind of methods. The problem with those methods is they only provide asymptotic convergence, and they also DCCP, for example, is a solver, a very nice solver, but they require some external black box solvers, and I'll talk a little bit about it when we go to experiment section. And then there are proximal point type methods. So one of it is our past work, and there is also some other work on this kind of methods. So these methods, as I said before, as I was mentioning to Cristobal before, these methods don't exploit the structure of the constraint that well because they deal with a very general problem. They don't necessarily exploit the structure of the constraint. They require a little bit stronger constraint qualifications, which may not be satisfied for this problem. So in a sense, we would like to get something that can exploit the structure and really go to really give us competitive rates and with not that restrictive constraint qualifications. Okay. So also there are some L0 norm constraint problems. The L0 norm constraint optimization one is like, of course, the mixed integer programming. We know that it's very efficient for small scale problems, but when you scale of the problems becomes large, then these are problematic. There's also hard thresholding algorithms. So these algorithms, they directly deal with the L0 constraint, but they also require some assumptions like restricted isometric property, which is probably not satisfied in all cases. So we don't want to impose those assumptions, but we still want to solve this problem. Okay. So our contribution is to, we propose here a level constraint proximal point method. Okay. So this is like a proximal point method, but for a function constraint problem. We prove is asymptotic convergence to the KKT solution. So we prove that the KKT multiplier will exist and under some mild constraint qualifications. And we can get to that KKT solution asymptotically. And then, as I said before, we also are interested in complexity results. So we provide improved iteration complexity results to reach an epsilon approximate KKT point, and I'll define what is an epsilon KKT point means. So basically, we deal with this problem in the case when psi x can be either convex or non-convex, smooth or non-smooth, and deterministic or stochastic. So any combination of these three categories. So do you have a total of 8 complexity results? Okay. And I like, because no matter whether the objective is convex or non-convex, the problem is essentially non-convex. So you get the same kind of convergence results. Okay. And in the smooth deterministic case, you'll get order 1 or epsilon, and the non-smooth stochastic case, you get 1 or epsilon square, where you will see the constant of non-smooth, like multiplier to the 1 or epsilon square, will increase when the problem becomes non-smooth or stochastic, and this one will be summation of both. So it will be a unified complexity result. So we can deal with all kinds of problems here.
Digvijay?
Yes.
So what is, I mean, the analog of unconstrained setting for your algorithm would be minimizing the norm of the gradient?
Yes, minimizing the norm of the gradient square. Yeah, so gradient square.
So the complexity there for near stationary points, is it like 1 over epsilon squared?
For non-smooth, yes. For smooth, it is 1 over epsilon. So complexity in the sense like gradient, like complexity of gradient descent. So this algorithm you will see is very kind of similar to gradient descent, but it does something little bit clever. So in a sense, it becomes the same complexity as gradient descent. So one can, like, a question that I had in my mind is like, can you implement an accelerator method for this kind of setting? And like there is a paper by George Lan and Gadimi, which deals with this like accelerated method for non-convex, and they improve some dependence on Lipschitz constants. But in terms of dependence on non-smoothness and stochasticity, it's the same.
I see. Thank you.
Yeah. Yeah. So that is like acceptable, because you would expect that like Nesterov acceleration will only help you with respect to the smooth terms, not non-smooth and stochastic terms. So let's see what is the main algorithm here. So I'll go a little bit into the details. So we are given this initial solution x hat, and eta is our constraint, like right hand side of the constraint. We start with an eta naught, which is strictly less than eta, and we gradually increase those etas to reach lower approximation of eta. So basically, you can say that these delta k's are positive numbers, and eta naught plus summation of delta k is eta. So eta k is a monotonically increasing sequence to eta. Okay, and that's why we call it a level constraint, because these levels are imposed sequentially as you go. So basically, bigger and bigger levels means we relax the constraint. And what is this GK? So GK is a bit different than G itself, in that we keep the convex term G bar as it is, and we linearize the H part. Okay, we linearize the H part. So at let's say a current like given point xk minus 1, when k is equal to 1, that's just x naught, but we do it sequentially. So if you see now, this linear approximation of H is a lower bound on H because of convexity. So given that it is a lower bound, gk is an upper bound on G itself. So that's what I'm saying. Gk majorizes G, but this linear approximation is exact at the current prox iteration xk minus 1, current proximal point of the iteration. So at that point, gk is exactly G of xk minus 1. So we basically get an upper bound on G, which is exact at the current iteration. Okay. And basically what that does is that because gk of x is an upper bound on G and eta k is a lower bound on eta, gk of x less than or equal to eta k is a convex subset of a non-convex set. Okay, gx less than or equal to is a non-convex set, and gk of x less than or equal to eta k is a convex subset of that set. And I will show you some figures later on, and you can see like a simple 2D demonstration of what is going on here. And in the objective, we add a proximal point term. Okay. So and we want to solve this problem now. So essentially for current discussion, I'll only say that we just need a feasible solution xk of this problem. Okay, I'm not necessarily imposing optimality right now. Then I'm saying what can we say about this feasible solution xk. So one thing we can say out of these is that we will generate a sequence of feasible solutions if we keep on going like this. So there are some assumptions that we impose here. So as I said before, eta k is an increasing sequence, and you start with a point x hat, which is strictly feasible, right? If it's strictly feasible with respect to eta, you can just choose eta naught, which is like between G of x hat and eta. Okay, so eta naught is not necessarily a very critical parameter, but basically you need a strictly feasible starting solution, and that is easy to find in the application that we are considering. Okay. So it is also easy to see, then we will generate a feasible solution part. Why? Because let's say xk is a feasible solution for the current iteration. So gk of xk is less than or equal to eta k. So when you go to the next iteration, gk plus 1 of xk is just G of xk, because xk is a prox center for that iteration, and at that point the approximation is exact. But G of xk is by default less than or equal to gk of xk, because gk is always an upper bound on G, and this is less than or equal to eta k, but that is strictly less than or equal to eta k plus 1. So essentially what we get is that for the k plus 1th iteration, because of this strictly increasing level, xk is a strictly feasible solution. So each successive subproblem will have a KKT solution, x bar k, and a Lagrange multiplier y bar k. So even though these convex subproblems are generated dynamically, you can ensure that they always satisfy KKT condition. Okay. Right. So, but the thing is, one can expect as you go along, when you reach a boundary of the non-convex set, you can say that maybe the Lagrange multiplier will explode, and we say that no, it will not under some conditions, which are again satisfied for these kind of problems. Okay, so we will discuss this very briefly. What is the second assumption? So second assumption is that we should be able to do an efficient projection on this gk of x less than equal to eta kz. So gk of x is basically, as I mentioned before, it's linear function plus g bar. So what we are essentially saying here is that g bar x is a simple function to project on, and that assumption is also satisfied for the application we are considering. So in our case, g bar is an L1 norm. So one knows that projection on L1 norm you can do in order d log d time. But what about projection on L1 norm plus these linear functions? So it turns out that with little bit of effort, you can also show that you can do an efficient projection on this kind of sets. Okay. So the if I have to give you a very brief idea of what we are doing here, so the KKT condition, we know that these kind of problems, the sub problems that we will generate, they will satisfy the KKT condition. So we start our analysis with that. So the KKT condition stationarity is given in equation 6, and complementary slackness is given in equation 7. If you look at the stationarity, it basically says that when, like, there are three possible situations. Xi is the ith component of x. If that is greater than 0, then you will have one type of equation in the because of the subdifferential. If it's less than 0, then another, and if it's 0, then you will have something else. It turns out that you can write this xi of y in a compact fashion, okay, like this. These three cases you can write it in a compact fashion. And now you want to look at the equation 7, which is the complementary slackness. So one thing I should say that when y is equal to 0, this is not a very interesting problem, because when y is equal to 0, that means this constraint is basically can be removed, and just unconstrained solution will be the solution. But in that case, obviously v is the solution. So the only thing we have to ensure is that v is a feasible solution, which you can do easily. But in most interesting cases, v will not be a feasible solution. So in that case, y will be non-zero because the constraint will be active. And as I said, the constraint will be active. So you want to solve this Ly is equal to tau problem. That's when the constraint is active. And you can use this form of x of y to write Ly. And it turns out that this is just summation of some piecewise linear terms, and the number of pieces is of order d. So you can find the actual solution in order d log d time by looking at the places where the pieces change the direction. Okay, and that is easy to compute. So basically, this shows that there is a near linear time algorithm to do projection, and given that evaluating these constraints and everything else generally takes order d time. This is something that we can think of as part of our oracle complexity. So that's why there is an efficient projection oracle for this problem. So now I want to give you a simple demonstration of what our algorithm is doing. So I am going to impose another condition on xk. Earlier I said that it should be just feasible, and if it is feasible, we'll generate a feasible solution path of all feasible solutions, right? Now I am saying that it's not only feasible, but it's also optimal. So it's equal to x bar k, which is the optimal solution for the sub problem, which is a convex sub problem. By the way, this gamma has to be greater than mu so that we can solve this problem, just to make sure that we are on the right page. So because of, one can say that because of the strict feasibility of xk minus 1 and optimality of xk, we know that psi k of xk should be minus 1 is k of x on psi of xk. What I am essentially saying is that psi of xk is a monotonic decreasing sequence under the assumption that xk is not equal to xk minus 1. So the successive proc center changes. And not only that, we can say that summation of the norm square of the differences of the successive iterates is bounded above by this kind of term. It's very simple. You just write this equation and then the telescopic sum. Okay. Uh, and if you know that psi is greater than equal to psi star on your feasible set, which is what you would do, which is a reasonable assumption to make in case you are solving a minimization problem, then in that case, this summation is upper bounded for any k. And essentially that means that xk minus 1 goes to 0. Okay. So what we are essentially saying is that if your xk is equal to xk minus 1 in some limiting case, then you have found a fixed point of this system, because now you are kind of stuck at xk. Every time you're inputting an xk and you're getting xk out. And this fixed point turns out to be a KKT solution. So it is not that simple. When you go to the limiting case, one thing you really have to make sure is that these dynamically generated subproblems have this bounded dual even when you go in the limiting case. And that we can show using an assumption, constraint qualification assumption like Mangasarian from Ovitz constraint qualification, which was proposed in our one of our old paper. And we use that assumption to also get this kind of convergence results here. And MFCQ is a very classical constraint qualification that people have used. It's fairly generally satisfied for many problems. So here, for example, MFCQ is satisfied for this CAD constraint. So continuing with my demonstration, I made 2 points here, like this a monotonic decreasing sequence, and you have that xk and xk minus 1, they converge, the distance between them converge to 0. So this is a simple demonstration with a SCAD constraint in 2D, just so that we can see. Let's say you start with the point 1.9 comma 0. There's nothing special about it. I'm minimizing a quadratic function, which I'm not showing here. The white region is a feasible space. Okay. So as I said before, you will generate a convex subset of this non-convex set, and you reach a new optimal solution 0 comma 2.17. The objective value has decreased to minus 12.66. Okay. Now you go to 2.17 as your next proc center, you generate another convex subset, right? And you reach another optimal point 0 comma 2.88, and the objective value is decreased again. And you can see the distance between the 2 points has also decreased. And one can expect that this is reaching this extreme point here, and that's what is happening. So if you 2.88, you do another convex subset, you get another 0 comma 2.99. The objective value is still decreasing, and the distance between the points is decreasing and is rapidly approaching this extreme point here. So basically what I'm saying here is that and this point will later on turn out to be the KKT point of the system. So it's a descent algorithm and it converges to a KKT solution. These are the two nice properties. Okay. But you don't necessarily need an optimal solution to solve this problem. Okay. So essentially what we want to, in the first case, I told you that you can just take a feasible solution. In the second case, I told you like you not only need feasible but optimal solution, you can get these additional properties. But in order to get a KKT solution, you don't necessarily need an optimal solution. You can deal with something in between. So earlier I said like x bar k is the optimal and assume xk is x bar k. Now I'm saying that xk not necessarily be x bar k, but it can be a stochastic solution with respect to randomness, which is like denoted by pi k. Okay. If you take the expectation of the difference between the two objectives of the subproblem, should be bounded above by distance to the optimal solution plus some zeta theta. So if you see, let's say you start with xk minus 1, which is a strictly feasible solution for your subproblem. X bar k is an optimal solution. So it's like starting solution like x naught minus x star. So this kind of convergence rate you would expect to achieve from some kind of deterministic gradient based method, right? What is this zeta k doing here? Zeta k is basically accounting for errors. Errors arising from non-smoothness or the stochasticity, okay? And what I'm saying here is that this zeta k, this rho should be between gamma minus mu. So gamma minus mu is basically the strong convexity parameter. And if this zeta k is, let's say, summable, so the errors, even though they accumulate, summation of error is less than infinity. Then we can make sure that in the limiting case, the limit point of this algorithm will be a KKT solution almost surely. So in the deterministic case, it basically becomes that you can just remove the almost surely part due to zeta k, and you can say that, and you also remove this pi k and expectation, and in that case you can get it's actually a KKT solution. Okay.
DJ,
Yes.
how restrictive is this like summable error?
So it's not. So as I like, of course, in the asymptotic case, there is no point of talking about complexity, right? Because the complexity, basically, there is no point. So if you solve the subproblem using large enough number of iterations, then you can make sure that the errors due to this kind of how do you say non-smoothness or stochasticity, they can be summable. But it's where it becomes important when you want to do complexity analysis, and we can show that it's not that like you can essentially use similar kind of condition and you can still get complexity result. In that case, of course, you don't need to sum it to the infinity, because there you will have a different kind of challenge.
I mean, if I understand correctly what you said, you're saying like if I spend more effort per iteration, I can reduce this zeta k so that...
Yeah, but that is for asymptotic convergence. So later on we'll show that if you have, let's say it's zeta k going from k is equal to 1 to k, so you don't necessarily care which one is bigger or smaller. You will care the summation is small.
Okay, thanks.
So you can keep it as a constant. In order to, and if you keep it as a constant, then in every iteration you will put the same effort.
Yeah, of course.
Yes. So we will see that. Okay. So we talked about asymptotic convergence, but we also want to talk about some Lipschitz-like property, like some convergence rates, right? That's the interesting part. So in that case, I would like to introduce some Lipschitz-like properties so that I can talk about convergence results. So in a sense, our objective has this stochastic form. Okay. The xi is independent of x, its distribution is independent of x, and you just take an expectation objective, the standard stochastic program, standard from stochastic optimization literature. And this expectation objective satisfies a Lipschitz smoothness term and a non-smoothness term. Okay. So if your L is 0, then it's non-smooth. If M is 0, then it's Lipschitz smooth. If both are there, then you can have smooth and non-smooth components. Okay. Right. So essentially our objective can be smooth or non-smooth, and it is also stochastic, or it can be deterministic if you don't care about the expectation. And we also impose that the H is a LH Lipschitz smooth function. Okay. So earlier we had only, for asymptotic convergence, we only required it should be continuously differentiable, but now we also require it to be Lipschitz smooth. So there should be X here. That's my bad. Okay. So typo. And that is required for convergence. I think without that you cannot get convergence to KKT solution. That's my understanding. Probably it's can be relaxed, but I don't know as of now. So okay, this is a bit dense slide, but what we are doing here is we are providing a complexity for LCPP method. So complexity result for LCPP, they will always depend on the subproblem solver that you have used, right? So here we are using a very simple algorithm called ACSA by Kadimian, and the reason we are using it is because it gives us a unified complexity result and makes our analysis much cleaner. But what I'm showing here with this bullet point is that instead of ACSA, we can apply any projection efficient solver in practice. Okay. In fact, when we solve the sub problem using in our experiment, we solve it using first order approximation in which you do some kind of line search and then you get really fast conversion. But in order to do complexity analysis, this method seems to be giving us a very compact way of analyzing this. So to answer Cristobal's question, here I'm saying that run ACSA, which is a first order method, which works on this kind of projection oracles. And because we have efficient projection oracles, you can run it easily. Run it in every iteration k, run it for tk iteration, starting from xk minus 1, of course. And because it does projection, it will definitely output a feasible solution. But the number of iteration, if you see, if your m and sigma are 0, so there is no stochasticity. So by the way, sigma is the variance of the stochastic gradients. So standard deviation of the stochastic gradient. So I should have mentioned that. So if your m and sigma are 0, then and this beta is a constant in that case. So essentially what we are saying is run it for a constant iteration. So you do constant effort in each single iteration, right? And set your gamma as per this setting. And in that case, you will achieve an epsilon kkt point in order in k iteration, where like epsilon is order 1 or k. Okay. And so basically in k iteration, if you put a standard effort, a constant effort, then it becomes you achieve an epsilon solution in order k iteration, where epsilon is order 1 or k basically, right? Right. So in the non-convex case, your mu is greater than 0, so it's a weakly convex function now. In that case also, you can, for deterministic part, you can keep it as a constant effort. And so essentially, whether the problem is convex or non-convex, you achieve an epsilon solution in order 1 or epsilon iteration. But when the problem is smooth or non-smooth or stochastic or the summation of those terms, then your like the effort that you put in each single iteration increases a bit. So you need to run it for order k iteration in each single iteration, and you run k of those to get order 1 or k kkt point. So basically you need k square iteration to get 1 or k kkt point, or rather you get epsilon solution in order 1 or epsilon square iteration. So that is how we analyze the complexity, and the reason we could do all these things in such a compact way is because we use this ACSA method. And we also use the criteria that we have, that I told you about, this criteria. We use this criteria as our guiding principle to solve these sub problems in a methodical way. Okay. So very quickly, I'll do some empirical discussion of empirical studies. So here we have some loss function Li. I think it depends on the kind of problem that we are solving. So the classification problem, we are using a logistic loss, and regression, we are using simple linear regression. And we are using the 6 different data sets, right? And you can see the dimensionality and like this training size and testing size. We generally train our problem on this training examples, and then our reported results are for tests. Okay. So first we do some comparison with an existing solver. I told you about DCCP. So DCCP is a solver developed by Stephen Boyd's group. It's a general purpose solver, but like for solving these kind of non-smooth, non-convex problems, they convert it into simple enough convex subproblems, and idea is similar, but they use idea is not exactly similar. They generate a little bit different convex problems, and their design of algorithm in that sense is quite different. And the way they solve those convex subproblems is using interior point method, for which they require a linear system solver in each iteration. So one can imagine that that is good for MNIST kind of data set, which is a small data set in small dimensions. But if you would go to a big data set, then it would just kill you, this linear system solver. And that's what happens. In some cases, it's good, but in some cases, before it even finishes first iteration, the LCPP already finds a very optimal solution, and which we would expect from a first order method, because it would give a very good solution very quickly. So that's that. So, and then the comparison with the sparse regularized model. So now we want to also compare with lasso and also the algorithm called GIST, which is used for this regularized problem instead of constraint problems. So as I mentioned to you, lasso being L1, it has problems when your number of non-zeros are large, then like it really overfits and it does not do well in the testing set. So the bias introduced is kind of large. And GIST and our algorithm, they perform similarly in some data sets. LCPP performs better in some data sets. GIST performs better, but they are both very competitive. Okay.
Digvijay,
Yes.
you're evaluating the prediction performance of the
Yes, testing
right?
area.
So,
Yeah.
so I mean, I can imagine that lasso is like way easier to solve that these other models. I mean, how does it compare in terms of running time? Do you have any idea?
So it's not too different, but I think you're right. Lasso has a scikit-learn library which they have developed forever. So it's quite quick, but our algorithm is not that slow, because I forgot to tell you, we run this method called spectral GD. And this spectral GD does something very clever. They use these Bradley-Bolen step sizes, and these are like adaptive step sizes which really solves the problem very quickly. So you don't necessarily need to worry about even setting that TK at all. Like you just do it just like that. You run for, let's say, 10 iteration, you already have a very like good enough solution that will give you convergence.
So it might be that it's actually comparable performance for.
Yeah, it's possible. I didn't really see plot it that way, because we wanted to plot same model for same problems. So that's why we compared like DCCP, because that was the solver for this kind of constraint problems. But it's good that probably it will be worth mentioning what is the runtime of lasso versus our problem. Yeah, something to do more experiments on. So in conclusion, I think I'm just in time. In conclusion, we propose a novel proximal point method for this non-convex optimization with non-convex sparsity inducing constraint, can be generalized to a general enough problem. We establish the asymptotic convergence and also the convergence complexity to achieve an epsilon KKT point. There is we also provide an efficient procedure to do projection onto the sub problem for the application that we're considering. And that's why we can really implement this LCPP for large scale problems, optimization problems. And numerical experiments show efficiency of this method with respect to large scale sparse learning. Thank you. And please, if you have any questions, let me know.
Thanks, Digvijay. Very nice talk. Very nice result.
Thank you.
Are there any questions? So I have a very basic one regarding the. So it actually has to do with the sort of criteria. I mean, in the sense that you're looking for stationary points. And you mentioned in the beginning that the motivation of these models comes from statistics, right? So what I was wondering is, like, I'm assuming that those statistics papers are assuming that you find the global optimum of this non-convex program to certify that you have certain prediction accuracy. So what happens?
I think so, yeah.
Stationary
I think so. Yeah, so that's a tricky question. like it's a stationary point. It's not even a local solution, right? So what do you do? Uh, in that sense, there is definitely a gap between statistics and optimization. Uh, but it like people then basically resort to experimental results to show that it definitely does perform better in terms of testing error. So it's doing something significant compared to like standard lasso.
Yeah, your results show that definitely.
But that's like way of saying that okay, we don't know what does that mean, so we can just say what happens to a stationary point. Actually, this is probably an area of research. Maybe I should do some more study on this. But people in statistics have already started looking at these kind of problems where they say, now if you have, instead of a global solution, if you have a local solution, what can you say statistically about it? But that's not my area of expertise, so I haven't really read too much on that area. But I definitely know like some professors in Georgia Tech, for example, were looking at this kind of a problem. Being a school which combines statistics and optimization, I think yeah,
Yeah,
probably they are out of their silos. Yeah.
right. I mean, the other question is, I think you answered it, but I just want to make sure. So this algorithm is optimal from the stationary points perspective, right? Um,
Like in terms of non-smooth and stochastic, yes. But like an accelerated method, when you have smooth problems, they can get little bit better. We don't really know what is optimal. I think George Land gets something like grad square less than epsilon for unconstrained problem, for example, grad square less than epsilon in epsilon to the power 2/3, better than 1 over epsilon, right?
that's Gadimian Land, or is it?
Gadim Land paper when they show like accelerated method for non-convex optimization, non-convex and stochastic. So I think before that people were thinking that the accelerated method don't really work because they are unstable and stochastic, they can't handle stochasticity. But they show that they can do something better. But of course, like implementing that in this setting is a bit tricky. Uh, so I'm not really sure, right? So one thing that you would have to do is that you would have to, in the design of algorithm itself, right, you solve these sub problems, for example. So you would have to linearize this objective so that it really becomes something like gradient descent. Right now it's a proximal point. So if you are going to relax the kind of sub problems you're going to solve, then what happens to the outside complexity? Because now you're solving relatively simple problems, right?
But you
So
can also accelerate proximal point, right?
ye,
92 paper.
yes, you can accelerate. You can of course you can accelerate proximal point, but right now I don't. Wait, what paper are you talking about? 92?
Osman Güler, 92. He has two papers on proximal point. One who shows, like, 91 paper shows the standard convergence rate of 1 over the sum of the step sizes.
Correct.
The
Yeah.
92 paper shows an acceleration of that.
I see.
So it might be
So
helpful.
might be helpful. Yeah, I can look at it certainly. Very nice suggestion. But essentially, what I was thinking here is that okay, proximal point by itself you can't do much because you're already solving a very strong problem. Maybe this 92 paper has some more ideas. But then one thing you can do to really make it look like gradient descent is to linearize this objective. And now if you think of gk of x less than equal to eta as a fixed set x, then it just becomes a projection, right, of this gradient descent. Then what do you do? Like then you'll have to construct another sequence and do all those kind of stuff. So first you'll have to establish the complexity of this gradient descent. I believe we answered that question in the next version of our paper. Okay. And in that version, we also get rid of this feasibly like a projection requirement of the G bar. So we can deal with more G bar, more general G bar. But this is going to be for smooth problems. And because it's for smooth problems, it really makes sense to really see now whether you can improve the complexity by accelerated method, because because in smooth problems, because of this Gaussian land, you would expect that something like this would happen, like something better can be achieved. So yeah, that's where it's like there's a lot of open questions here, and it's I think only in past two or 2.5 years people have started looking at function constraint. And yeah, it's a very as you said, there are a lot of things to do here.
Yeah, I mean,
from statistical point of view, from optimization point of view, everywhere.
right. So something else I was going to point out, I mean, sounds like a hassle, but when you're considering KKT points, there's also these sufficient second order conditions, right? So if you assume higher order smoothness, you can even aim for like not just stationary points, but maybe things which have also the sort of right concavity or convexity, right?
Yeah, there are those, and there are also like I think in the unconstrained optimization literature, there is like something that has become very popular is like KL property, and they say that a lot of functions we see in the literature they satisfy KL property. So in that case, you can achieve global solution even though it's a non-convex problem.
Right. But what
So
kind
in that case, then like for function constraint case, what does that mean? That's also another question that was there on my mind. Like it somewhat is related, like you want to achieve some kind of global optimality. Like this second order condition is more classical, but I feel like maybe the scale stuff might be more interesting provided that people have already looked at it and they have already made a case that scale stuff is important because a lot of functions that we see in the real life, they are KL like, like there's a lot of connection to neural networks and stuff like that. So in that sense, KL property for KKT conditions seemed something interesting in by itself. So
I mean, the other thing is that since you mentioned neural networks, it seems that at least the way people address it right now is like an unconstrained problem, right?
yes.
It's already non-convex and complicated. So if you could say something precise about like constraining the neural network somehow, maybe who knows what else you can do, right?
Yeah, and also like this kind of stuff, of course this is like a bit more very very advanced stuff, but in neural networks, let's say if you can put some kind of constraints on the objective loss and minimize some kind of risk associated with the loss, right? Now you might introduce some things which are robustness of the neural network kind. Because we know due to Benthal and Nemrosky that these kind of risk measures, they introduce some notion of robustness, at least when linear uncertainty sets are concerned on convex problems. But then you would expect that because of these risk measures, you would introduce some kind of robustness. So those kind of experiments can also be done, but it's also very challenging to do those experiments because in those cases the constraints will also be stochastic in a sense. And stochastic constraints, I think the only thing I know about stochastic constraints, non-convex, non-smooth, is our last paper where we introduced these strong feasibility constraint qualification. Otherwise, I don't know a provable method. Maybe there is something that you do experimentally, like solve the subproblems to good enough accuracy and put in that engineering effort and also like computational effort. But from algorithmic design point of view, non-convex, non-smooth with stochastic constraint, function constraint, that seems quite challenging by itself. So yeah.
Let me ask if there's any other questions at this point before we finish. Okay. If not, let's thank Digvijay. I don't know if, however is possible by these means, but I'm just going to pause here.
Yes.
Thank you very much again.
Thank you.
Great talk.
Yeah.
And we'll just then conclude.
Yes. Yeah. And I'll send you an email about Friday. Okay?
Ok, all right.
Bye.
Chao a todos, gracias por conectarse.